All right, so what I want to do is check to see if the meter is working. Well, I'm sure the meter is working. I mean, if I can use it effectively and properly. So I think I'm gonna try and take the source voltage to make sure I'm getting 3 volts. So my power is off. I'm just gonna use these little sticks again. I'll get something better soon, hopefully. So I have my positive and my negative, and these are just the ends of this guy that we had cut off, the resistor. So I have these two in, positive, negative. I'm gonna plug in power. Make sure nothing is hooked up. Right now, the LED should not be able to turn on. Okay, and then I'm gonna turn on the meter again. Let me move this over. So I have my little meter, and I'm gonna put it back on voltage, or direct current, I should say, voltage. I think I used the lowest number, although I guess that's not the lowest number. This is like micro or milli. I'm not sure what. I should look this up. But I'm just gonna put it on and see what happens. So that's on, power's on. Let's see, positive. Okay. It's really bouncing around. I'm guessing there's not a solid connection, so I'm gonna plug out the power, and I'm going to just make sure it goes in properly. I don't like how these feel. Let's see what else we have over here that we could use. I think we have no. Okay. I have some of these pins that come with some components. I think these came with like an accelerometer or something. So take 2 out. All right, there's 1 and 2. Okay, hopefully this is better. All right, so I'm gonna make sure my power is off again. It is. I'm gonna put 1 in. This feels a little better. Although you'd think they would stick up more, but I don't know. All right, you can kind of see them. And my little cap. So yeah, there's 1 right here and 1 right here. So let's see. I guess I'll plug in my power again. Here we go. Positive, negativo. All right, and let's see what happens. Okay, now it's much more stable. So I guess it was loose before. So it looks like it's 3.1, 3.15. It's supposed to be 3, so I guess that makes sense. And now the amps is what I couldn't do before. And I don't know why, unless the amperage was so low. But I guess in that case, no, it was showing like a 1. I wonder if I have to move this here, like move this over, because it does say A here, like for amps, and this side there's also an A, but it has, I guess, voltage, resistance, and milliamps. So I don't know. Let me try it out and see. So let's go to the current side, and I guess the lowest number, or is this the highest number? Maybe it's the highest number. I'll use the highest number. Let's see. Okay, now we're getting something that makes more sense. So we're getting like 1.9 amps, if I'm reading that correctly. Because it's not resisted in any way, so I'm guessing that's the source. And I'm pretty sure it said 3 amp max. So at least we know, hopefully then, that it's 3.15 volts or so, and 1.9 amps. All right, so I'm gonna turn this off. I'm gonna plug up my power. And now I want to take this little guy out. Sorry, there's 1 and 2. Okay, now I want to try and rebuild my circuit and see if I can get it to work with the meter again. And if not, I'll just move on to the more transistor testing, which is kind of what I want to do, but I need to kind of cover the basics too, or learn the basics myself, I should say. Excuse me. Okay, so we have our little dude going in there. Positive. Oh, you know what? I could just leave him sticking up, and he can be my new positive terminal, right? My little tower. And the switch is not activated, so I guess I should take that out and stretch this guy to 15. It doesn't need to stretch, actually. I could just move the whole thing. So he's going to plug into 15 to get grounded. Oh, but there's a gap here too. What did we have there before? I don't remember taking that out. So I'm just going to take this out too then. And just make it very small. So this guy will move down. LED will take positive voltage. It's a long one. From, let's say, 20. And then pass it to the wire leading to the ground on 23. So we should be able to connect positive to negative here to create the circuit, and it's resisted, so this guy should be fine. Even though this thing is also has some resistance to it. This is where I guess data sheets and details and stuff really is sort of a requirement and good practice. So this is probably not the best practice. All right, so I'm gonna do voltage again, which I guess I need to move this back. Let's see. Okay, so voltage. I just go for the smallest looking number, and I'm guessing these are actually smaller, like micro or milli. Well, micro is this symbol, so this is milli. Okay, that makes more sense. So this is 10 amps, 200 milliamps, 20 milliamps, and I guess you could say 2 milliamps or 2,000 microamps. I think we are learning. And this is some crazy amount of voltage, I guess, and the 220, 2,000 milli, and 200 millivolts. Cool. All right. I'm pretty confident because, yeah, I remember this is micro. So let's see. So let's go down to then the voltage is going to be in the thousands of millivolts because, 2 millivolts, 2 volts will be like 2,000 millivolts. So that sounds like it lines up well. Let's see what happens. So positive to negative. Oh, I didn't plug in my power. Okay, power going in. Make sure nothing is connected. Okay, positive and negativo. All right, and positive and negative. So still not getting any kind of illumination from the LED. It's so odd. And I don't have any voltage on the reading. Let's turn it down and see. I don't know. All right. And this is direct current. All right, let's let's try the meter. And I did connect this the right way, right? Yeah. Positive. Oops. Okay, I think he's okay. All right, so let's swap this over and try getting the amps out, 2000 micro amps. All right, so we have our positive. Hey, now we have something happening. That's so weird. I don't know what the difference is. I like that he's lit up. All right, so now we have 20 milliamps. Okay, I like that he's alive. Hello, friend. But it shows 0.0, it shows like nothing, which is weird. I'm pretty sure this is a 100 ohm resistor. Or is it 1000? I think it's 100. Yeah, I had it in this little bag. 100, and then it's not a 0 at the end, it's an ohm symbol, which is probably not a good decision by me to write it that way because it looks like 1000. But I should really just put 1K for 1000. Anyway, so it's 100. I like that he's lit up though. I just want to keep doing this and look at him. Whee. All right, I'm just gonna move this up to 20 milliamps, I think. Still getting 0.01 or 0. So I don't know what is happening here. Maybe it's too low to record. Or too low to detect. Because yeah, if I go up to 10, I mean, nothing's going to happen here. So let's go back all the way down and see again. Yeah, I'm guessing it's way too low to detect. And I know that there is... I know two basic formulas, I think, from electronics. One of them I have to use a lot because we're in manufacturing and I have to kind of monitor our heat usage with electricity. So I know that volts times current equals the power or the wattage. I'm guessing that's important. Well, I know it's important for what I do, so it must be. And but that doesn't really help us here, because we don't know what the current is, right? We know the voltage. Well, last time we got the voltage. This time, actually, I don't know. So last time we could read voltage but no current. Right now I can read current but no voltage. So let's go back to current and see if we can get it working again, because that'd be silly. Okay, we get a 1, which I'm guessing is like over the... No? Okay. Okay, there we go. So we're getting the 2.9 volts. So we don't know the current, but we know the voltage. And we know the source voltage, and we know the ohms. So I'm pretty sure Ohm's law is volts or current. No. Yeah, volts equals current times resistance, which means I should get a pen and paper. Or just a calculator. Let me see. Let me get a pen. All right. I have returned. So power is still on here. I just need to be mindful of that. So Ohm's law, I should double check this too, but I'm pretty confident. V equals I, which somehow this means current. That's a terrible writing. I guess R, which is resistance. So V equals current times resistance, which means if we divide, or I want to divide the other one, I want to figure out my current. So current equals this divided by this, maybe. So V over R. So in my case, if we know that our voltage, now does this mean before or after? I guess it's after. So that's roughly 3 volts over 100 ohm equals, and we just move it twice, 0.03 amps, which is the same as saying, let's see, 1, 2, 3, 30 milliamps. So I think this sort of makes sense. So 30 milliamps. How do I read that? Oh wait, didn't we did read it? Oh, we didn't read it. No, it showed 0. It shows 0. So 30 milliamps. I mean, this guy seems to have a symbol. Let me make sure I don't. This guy has 20 M. So why can't he read it? He should be able to read it, right? 20 milliamps? That's less than 30, and this one is more than 30, so it's within the range, it seems. I have not the slightest clue. But let's try it again. I just like that we'll get to see it lighting up again. Is this still on the camera? I can't tell. It's not. Alright, let me move this over. Okay. So, positive. And then, well, now you can't see this. Alright, let's see. Yeah, I don't know what's happening. It says 0.01. I don't know what that means. Let's do 10. See what happens. 0.01. This guy is not very creative with all his symbols. Let's do 200. 0.01. Or 0.1, I should say. 0. This dude. And that just says 1. 0. I have no idea. So I was trying to just figure out what the reading is, but I don't know. I'm gonna have to research this and see. So I'll try and put that part on video too to learn from in the future. All right, so I want to find out what I was missing for my voltage recording and why it was failing. So it seems that we were able to, well, we didn't really get a good measurement of the current. It showed zeros. I guess I should look up the manual for that meter. But the voltage, I want to learn how to take voltage of a circuit, because I was able to do it when there's no load between the positive and negative of the power source and the ground, but which was like 2 amps or whatever it was, 2 point whatever amps. But I want to be able to, sorry, it was 3.15 volts. That's what we're talking about. So it was 3.15 volts, and I want to be able to take the voltage of the actual circuit, which I have not been unable to do. So I'm going to just look up, I guess, how to measure voltage in a circuit, I guess. But this is all like talking about how it connects. So this is what I did before. Connect the negative lead to the ground and positive to the input, which that works fine. But if it's, well, I guess it would still work even if it was connected to my LED and stuff. It's just it will be in parallel, which I thought that mattered, but maybe it doesn't. Let's look for a picture. Okay, this one looks interesting. So let's try and blow this up. So this is negative and this is positive. So yeah, this is in parallel. This is in series, right? But this is parallel because we have the power going to the resistor, but the power is also going through here. So there's two paths to ground from the power source. So they're going, you know, in parallel. This is one, and this is the other path. I hope you can see the mouse. So I guess I'm supposed to do it this way. I thought it had to be in a series. I thought I need to be like, you know, in between to get the voltage. But I guess for voltage, it's like this. So let's look for current. How to measure current in a. I'm gonna put DC circuit because I think it's different for AC, or I have no idea. Okay. So yeah. This is what we did, I think. So we got it right for the current, but not for the voltage. Yeah, this is making a series because there's still only one path, right? So positive through our red, out our black, continuing to the light, and then there's a resistor here, but there's only one path. All right, so to measure current, we need to make it, I guess, like a part of the circuit in a series. And for the voltage, we need it to just not get in the way. We're kind of just like watching from a distance. We're voyeuristic. Voltage is voyeuristic. That's a good way to remember it. And for the current, you're, what's that word for C? You're, ooh, there's a word I'm thinking of. When you're part of a crime, not a collaborator. Ooh, what's the word? Let's look up thesaurus. Collaborator. No, damn. That's not what I'm thinking of. When you're guilty, essentially. Convicted? No. Culpable? Kind of. Convictable? No. Man, there's a word. But anyway. So voltage, we're just watching. I mean, not waste any more time. Voltage, we're just watching. And current, we are in between. All right, so that makes sense. And while I'm here, I guess I should look up Ohm's law to make sure I had that right. So I'm going to say how to calculate current from voltage and resistance. And I'm fairly certain that I was correct. So current equals voltage divided by resistance. Yeah, I think that's what we had. Yeah. So, well, we could have tested. So we had 3 volt. It was really 3.15, but I'll just put 3. And I think we had 100 resistance. Yeah. So this is 30. So milliamps. 30 should be anyway. You won't let me talk. Okay. 3 and 100. No, sorry. 100 resistance. But I want milliamps. Why won't it let me do that? Yeah, 30. Cool. So that part was good. We're almost at 1/10 of a watt, it seems, which is interesting. So I guess I should go and try record that now, and see if we can get a voltage reading, and then I really want to get the current reading because we only got 0. So I guess I should look that up real quick. It's an Astro AI something 33. I don't know. This one, AM33. Because $2,000 counts. What does that mean? Anyway, user manual, perfect. Oops. I don't think I clicked the right thing. Where did I go? User manual, English. Okay. So, measuring current, and there's 2 of them, which is interesting. I guess when we plug out the wire, maybe I didn't do something right. I thought that it was working. At least the light was illuminated still, but okay, measuring DC current. Enter the red into the first guy, which is how we have it for like voltage reading. And the black into the common terminal. That makes sense. And then we do, okay, well, they want us to test the leads, which I did not do. And then start from 10 amps. Well, I know the current more or less, what it should be. Turn the rotary switch to the 10A setting of the, I guess, current, DC current area. The screen will display zeros, indicating that the measurement function is a DC current from 200 milliamps to 10. Interesting. So mine should have read 1. I really should have this next to me when I do it. Wait, so I had it in the wrong one, right? Because I had it into this one. The first time I had it here, and it didn't work. Let's see. All right, measuring DC A current. Disconnect the power supply. Insert the red test lead into the second one, which I've always had it there, and the black into the common. Turn the rotary switch to the continuity test. Okay. Turn the rotary switch to the DC with the yellow font. I don't understand. The screen will display 000, indicating that the measurement function is a DC A current from 2,000 microamps to 200 milliamps. So will it not tell me how many amps it actually is? I don't understand. Damn. I'm not sure. But we can calculate, if we can read the voltage and the current. Sorry, if we know the voltage of our power supply and we know the resistance of each resistor, we could just use the math. But it would be nice to see it too, though. I don't know why. Here's accuracy. DC voltage, no. DC current. So the range is, I guess the minimum is 2,000 microamps. It has accuracy here, 2%, plus or minus. So it should be able to read. I don't know. Anyway, so we should try and record the voltage and see, and then I'll come back to this and try and do that again. But it's good to know that we have Ohm's law working, because that will help us a lot And now we can measure it like this and see what voltage we get. I guess it should be 3, the same as before. Um, so, and then this is how we did the current, right? So let's see how that goes. All right, so let's see if we can get this to work. I'm gonna put this resistor back on, and then see if we can finally get a voltage reading that doesn't kill our LED. So let me line this up. So that's in, and then I think this guy's a little too short. Okay. All right, let's plug in power and see if that works. So positive and negative. Okay, so we have our light. Now, let's do the magic. So, what was it? Voltage is voyeuristic. I remember the other one now. It was current is complicit. That was the word, complicit. Right, you're complicit with a crime. All right, voltage, DC. So if we stick it onto the end, does that say something? The light's in the way. Yes, it's 3.08. Perfect. Let me see if I can move this. I don't think that resistor is in very well because it's very shaky. All right, perfect. So that's 3 volts. Wonderful. So that works, and it doesn't mess up our LED. He's not working anymore. I'm guessing because he's very loose. Yeah. So let me plug it out. I don't like when things have a loose connection. Kind of dangerous, I think. Anyway, so that works well. So I guess I need to, this is a 100 ohm resistor. I guess I need to just get a longer one. So I should probably try and take the, let me get this out. This is a 1000 ohm resistor, but he has long legs. So at least he'll be good for testing, even if it's messy. But I won't need to worry about the security of it, of the connection. Okay. So try and dodge that light beam right here. All right, so let me plug in again, make sure it works. Yes, all looks good. And let's try and see again. So we have 3 volts on this circuit. There's a difference, though, depending on where I read them. I wonder what that difference means. We have 3. When I pretty much go from start to finish, it's also 3. When I do 3 to the LED, I assume I don't want to pass this to there because we'll be skipping the resistor and we'll create, well, I don't know what the resistance is of this guy himself, but I'm not going to try that because I don't know enough to do that. So if I measure the voltage, I guess that's still weird though. It should be 3 volts going through this thing, right? 1.8. And this guy? 1.3. Not sure what is up with that. I need to do some more research real quick. But you know what, while I'm here, let me try the... Oh wait, I need to be in series for the current. Alright, let's see. Let me plug this out. And real quick, I'm going to... Oh yeah, I don't need to do much. I could just stick him upwards. I'll stick him up. And I'm just gonna stick him into a different one. Because I really don't want to make the wrong connection. I don't want to make the connection from here, this side, to here, and have some sort of exploding LED in my face or something. So I'm gonna just safely take it from here, which is already resisted, and then it can go. So we'll kind of create a parallel connection here. But it's a series. So let's put it back on the which one is it? The current, right? Do the lowest current. Let's plug in our power. And let's see. Hey, we're getting something now. Although that doesn't make any sense to me because... Oh no, this is 1,000. This is a 1,000 ohm resistor. So hold up. What does that mean? It should be very easy math. We're just adding a 0, right? Let me turn off this guy. So we have... let's see. Move this over. I don't like this white background. I feel like it makes it hard to see. I need to get back to the black. I could swap that out real quick. I have a tablet here. I can just use that. I don't like the reflection, but all right. So we have we had current. I think this was accurate, right? So we have 3 volts over 1,000. So this should just be point. What's that? 0.003. Right? 1, 2, 3. I think so. And if we multiply that by 1,000, then we get 3 milliamps. I think that's how that works. 3 milliamps. Now I don't think we're reading that. Let's see, turn it back on. We're getting, well, that's microamps. I only see 1 milliamp. 1.35 milliamps. So what does that mean? That's like half of what we should have. Pretty sure I can test resistance on here. I'm gonna plug out my power. And I'm gonna take out this guy. And let's see if we could just test the resistance. So I'm gonna, this is the resistance symbol, so I'm gonna put it, it's a 1K, or it should be, so I'm gonna put it to 2000 and see what that means. So I'm just gonna try and, yeah, I need to get better at doing this. Okay, that's a pretty solid connection. So that's, yeah, it's 1000. So I don't understand how we go from 3 amps, 3 milliamps, to 1.5. I need to research that. But making progress. Now we're able to take voltage with some kind of value that shows up, and able to take current with some kind of value that shows up, even though they look weird. And the voltage, you know, how it was different between the different areas, I need to figure that out. So moving on, we'll see how it goes. All right, so I want to just get a bit more info on getting the voltage of the circuit and try and figure out what's happening with the current. So I'm just going to type in what's happening. So pretty much voltage readings different along circuit, I'm going to say. And then this little AI overview seems to be, voltage readings can be different at various points along the circuit because of voltage drop, which occurs across components with resistance. Meaning that as a current flows through a resistor, some of the voltage is lost, resulting in a lower voltage reading further along the circuit. Okay. Right. Well, that seems to be what's happening with us then, which would make sense. It's a resistor. So what that means is each component that takes or that has resistance will essentially consume voltage. All right, I mean that makes sense, I guess. So then the other thing was, if I use a calculator that we had before, it is 3.15, I think, was our volts. And, or was it 2 point something? I need to record it again and see, like with a load. May have been like 2.9, but our resistance right now is 1000. So if I want to calculate for that, why can't, does that let me do that? I need to refresh. Resistance 1000 ohms. Yeah, I mean that makes sense. 3.15. I don't need a calculator for that. But we're getting 1.3, I think, which is so strange. I mean, there just must be more to it. I wonder if the meter will, I guess, reduce the current. Will meter multimeter reduce current reading? Well, my multimeter is kind of poor quality. Well, I don't know about that, but I think it was like $12. So maybe that is an issue. Well, I'm going to just move on, I think, because I can come back to this part after, but I'm interested about the other thing that I had, the voltage split amongst components. I don't know what I typed before. Multimeter reading different voltages along circuit, I think. So let's, I'm gonna dive more into that and see now that I know that that's a thing, I just need to make sure not to circumvent my resistor and blow up my LED. So I'm gonna go back and just continue. I'm not gonna worry about the current reading right now. I'm going to probably just try and get into some more transistor type stuff because that's where I want to get to, logical evaluations, and then just build on it from there and see what happens. So actually, should I check real quick the voltage? Because I'm using 3 volts, and I'm only using it because it's the lowest that I could excuse me, use with my my power supply. So anyway, I'll just move on from now. All right, let's see if I can get some better readings or readings that make more sense to me now that I know a bit more. I had taken everything out and I thought I was recording, but I wasn't recording. So now we have a magical empty breadboard to start again. And between the video where I looked up the voltage drops and stuff, you know, the previous one, I spoke to a cousin-in-law of mine named Leonardo, who's like an electronics expert, engineer extraordinaire, that kind of thing. And he explained it to me a bit. I wish I could have recorded that because it's very useful. But I can explain my understanding of what he said, which is kind of what we saw. Voltages. I'm gonna plug this in while I do that. So real quick, so I don't forget. So if we have a resistor going from positive into the circuit, and then I'm gonna put the long leg, put it over here where we can see, into positive, bloop. And if we connect this to ground, then we make our circuit similar to what we had before. Here we go. All right, so that's a little circuit, right? Positive goes through the resistor into the LED, out to ground. So I'm gonna plug this in and see if he lights up. So 1 and 2. All right, so he is alive. So what Leonardo was saying is that since this is a series, resistor, LED are in series, the voltage will actually be different for each component. And some components, from what I understood, will sort of demand a specific voltage. And then the ones that don't demand a specific voltage will kind of like just get the remainder. So in this case, what we saw was, I think, 1.8 volts on the LED. And did I add it on paper? I don't know where that paper is. But if we have 1.8 volts, we should just check it now, actually. So I probably need to lift this up so that it doesn't get cut off like before. So I'm going to try to lift this up. And I'm going to move him over. And I'm going to put this guy right here. And I forgot again if I highlighted it, but this does say milliamps right here for this input, if you will, I guess. And over here it says 10 with a cap, well, just A, not milliamps. So this is probably for reading heavier current, and this is for less current, I assume. And it does say, if I plug this out, it does say 500 milliamps max for these two. So we should be far below that. We should be like at 3 milliamps, I think is what we were expecting, which is, excuse me, 3 volts divided by 1,000, which is this resistor. It should be this anyway. All right, so let's see the voltage and see if what he was saying adds up. I think it does, based on what we got last time. So I'm going to move this to direct current symbol to voltage. 20, since we're in low single digits. I got my red, and I got my black. So I'm gonna, well, I should leave this here. Okay. So I'm gonna do my resistor, which is 1.1. And then I'm gonna do my LED, which is 1.79. And then I'm gonna do from the end to end 2.9. That's different. Last time it was higher. I think last time it was 3.1, right? I don't know. All right, so we have 2.9 total. And then we have 1.8 roughly. And then we have 1.1. So yeah, I mean, that makes perfect sense. Let me turn this off. Get our little paperito. So if we have 1.8 volts, volts is what, capital V? Let's see, it's a capital V, yeah. Plus 1.1 volts equals 2.9 magically. So that's cool. So that means that when we have a series like this of components, these dots are just components. I don't know how to draw schematics, I need to look that up. Then if this is 3 volts like mine, then all of these will get a piece of the 3. And when we add them all up, then we get 3 volts. I did not know that. I am very curious as to who decides what each one gets. So maybe I'll do a quick test for my own curiosity and knowledge and practice, and see kind of how the voltage is split up, because it seems to me like it's almost random, or maybe it should be equal, or I don't know. Anyway, more to learn. So that's those are called voltage drops, which to me is weird terminology. When I read voltage across, I guess that just means between one side and the other of the component, but again, more to learn. So that's voltage. Now, for the current, the current was different. So I have my little stick that I can set up to take the current, because remember, voltage is voyeur. We can watch a functioning circuit, but current, we must. It was complicit, but maybe it's critical. Maybe it's continuous. I don't know. I need another phrase for that. But basically, we need to. Well, I guess the phrase is series. So voltage is taken in parallel, current is taken in series. So I'm going to add a pin here that I can use just to conveniently hold on to with my meter. Where's my little stick? I always lose him. Hey, there he is. So I'm going to put this in all the way down. Bloop. All right, so he's down there. And then I'm going to move the resistor so that we could power up this row 7. And the main goal here is I just don't want to touch the wrong, what do you call these, pins or legs? I don't want to touch the wrong leg and make a connection from here to here, blowing this up, because we'll be skipping the resistor. So I want to make sure I take it from this side. So I'm just going to pull the power from here into the resistor and then into row 7, and then I can safely touch here without getting anywhere near like this one. That's why I'm adding the little leg. And it's easier for me to just press against it with pressure and make sure it's like a solid connection. All right, so we have the LED, which maybe I'll stretch him a bit more to make it easier for me to interact. So I got him stretched a wee bit. So right now, if I plug this in, it should not work, of course, which I'll do that. So I'm going to plug in power and negative, bloop, and we have nothing because there's no circuit, right? The power comes from the power rail into the resistor, energizing row 7, but he has no way to get home, which is a gray cable. So he's missing, right, a wire, and our meter will become the wire. We shall restore the connection that he so desperately wants to create magical lights. So I am going to turn this on to not resistance, current, right? Current. What is the symbol for current? Is there a symbol for current? I guess the A for amps. So A, the direct current. And I'm going to do, excuse me, I'm going to do the micro amps. And I'm going to connect my red dude to the resistor and my black dude to the LED. Oh wait, to my post, right? So we have lights, which is wonderful. And now we're reading 1.2, let's call it 1.2. Okay. So if I turn off, let me try again. 1.19. I'm going to move it up a bit to milliamps. Let's see what he says. 1.29. That's a little different. All right, 1.29. So we have 1.29 milliamps, 1.3, 1.2 coming through here. And that is the current. I was expecting 3. And I was confused as to why we're not getting 3. But based on what Leonardo told me, I think I know. So let me get the paper. We had measured right now the amps equals 1.3 milliamps, right? Now the resistance voltage we know is 1.1 volts because we measured that. So if we use Ohm's law on this and divide it by the resistance, which is 1,000, we get 1.1 milliamps, which is a lot closer to this reading, right? This should be the same. And this is what I was missing before. I thought the entire, I thought the entire circuit should be 3 milliamps because we have a 1,000 ohm resistor and we have 3 volts supply, which we know it's really 2.9 by the most current reading. So this, right, should be 3 milliamps. But the idea here is that the LED itself does have resistance too, and the meter slightly, but the LED has resistance. And the series, so the voltage is split, right? So we might have like 1, 1, and then 0.5 and 0.5. Let's say we have 3 volts and we have 4 components. It might be split by 1, 1, 0.5, 0.5. Together makes 3. So they're different at each point. Maybe there's no guarantee that they're the same. But when we have a series and we have current, which I'll just put A for current, they're all the same. And that's the difference that I did not understand. So in this case, when we are connecting the resistor to, let's say it was connected to the LED. Let me connect it back together again. So this post, I can take it out. Okay. So right now, plug this in. Make sure I'm resisted. Yep. All right. Power and negative. My camera stopped recording, so my my resistor was plugged into the wrong post. It was in the negative, not the positive, so I had to adjust that. And then I realized that the camera had shut off. So now we have light, and so this is a series, right? We have resistor to LED. That makes up the series. That means that the current flowing through this entire circuit is the same. And we know that it's 1.1 to 1.3 milliamps. And we know that because we measured it, and the math also supports that. So we have 1.3 milliamps, let's just say, going through all of this, right, constantly, at a constant rate. However, the voltage, 3 volts, is not constant. It's split up in here. This guy gets more and this guy gets less, I think because he decides that he needs more. So this guy gets the leftover, I'm assuming. So what I want to do right now is just verify this fact by adding some more resistors and maybe removing the LED, which that was another good thing that Leo said, is just remove the LED and do testing that way. And I really should have thought of that, but that's why I'm a noob at this stuff. So if we do just connect this guy, we just have a circuit with a resistor. So we can start here, right? Let's try that. So I'm going to plug in my power and my my negative. So this is on right now. My LED is over there taking a little break. So let's take the voltage. Voltage. Okay, direct current. Put this little guy back here. And so voltage is on the solid one. Let's see what happens here. So now we're getting the full 3 volts on this one resistor, which makes sense. There's one component. We have 3 volts on the series. So he gets all of them, right? It's 3 divided by 1 component is 3. So now what I want to do is get the current. So let me turn this off real quick, plug up my power, and I'm going to just move this guy over so I can take the current. I'm going to add my little post in here as a way to grip onto it easily. Push him down. Oh, he just jumped. Did you see that? He's a magician. I need something to press it down easily with, like maybe this thing. Okay, I definitely need to get like some tools that make it easier to do this. Okay, so now I'm gonna move, put this guy on current reading. 20 milliamps should be fine because we should be at 1,000 about everything. Oh, you know, now we should see the full 30, I guess. So let's make our connection. Make sure it's on the screen. Or 3, I should say. And nothing's happening because I didn't plug my power in. All right, turn this off. Plug my power in. Bloop. And bloop. Okay. Now let's turn this back. I should raise up the camera some more. It looks a little crowded, right? Try and cover up the whole thing with the black background. All right, so we have our meter turned to current reading. Look, a little ant is on there. Be careful. And we have 3 milliamps of current. So it's exactly as Leonardo said it would be. We get the full well, I guess not full, but the math is very simple now because we only have the one resistor and we know the exact resistance on it. So we have 3 volts, we have 1,000 ohms of resistance, which makes 3 milliamps. Or if you want to say 3 volts divided by 1,000 is 0.003, and 0.003 is the same as saying 3 milliamps. 0.003 volts. Sorry, I am saying all sorts of stuff. 0.003 amps is 3 milliamps. So that works well. That's kind of cool to see. That's what I was expecting to see the first time, but now I understand that the LED has some resistance, and apparently it's not linear resistance, so it's not static. It kind of changes depending on the load. So that's stuff I don't need to get into right now. But this works well. So I'm gonna, I took the voltage already, I think, right? Yeah, I took the voltage. And we saw that the voltage drop, to use the right terminology, I think, across the resistor is 3 volts because it gets all of the voltage. Yeah, 3 volts divided by one component is 3. So right now I'm going to remove power, bloop, and then I'm going to add some more resistors in series. So we have one guy there, and this is kind of messy with all their long spider legs, like giant spiders. But I think it's just the simplest for me to just knock it out, and then later on I'll be neater and stuff. So I'm gonna do the next guy. You know what? Let me move this one down to the top. So this guy goes into number 2, and then we have another 1,000 ohm resistor who continues this series. Bloop, down. So now he's in. Okay. We still have our post right here that I can connect to for series. Right here. Connect these two. So I'm pretty sure these are both 1,000 ohm resistors, but we should, the math will tell us right now. The value will tell us. Actually, I could probably measure it like this, right? Which would be really helpful. So I'm going to turn this to resistance. And these are 1,000 ohms. I'm going to put it on 2,000 just because that's like a close number to it. And let's see what happens. That's reading 984, so that's 1,000 ohms, right? And that's 900 or 1,000 something. So these are both 1,000 ohm resistors. And another thing Leo told me to do is just take the resistance of the entire circuit sometimes. So if I do this, you can see that they add up, which is kind of cool. So resistance or resistors in series adds up very, very simply. There's no weird math to do. It's just 1,000 plus 1,000 is 2,000. So we know these guys are working and they're connected. So let me turn this off, plug in power again. Right now there's no connection, right? Because resistor B leads nowhere. It's just nothing in between. We need to make the circuit. So the power right now is going up through resistor A into resistor B, and then it's stuck here. It can't go home. There's no way to get to the gray cable, or I should say row 18 in, in general. So now we can take our current reading, right? So current over here, the A for amp, and we're going to be in the milliamp range, so 20 milliamps is a good number, I would say. And let's make this guy get connected. So there we have current is 1.5 milliamps. And that makes perfect sense because 3 volts divided by 2,000, or if you want to make it easy, 3 divided by 2 is 1.5. So that makes a lot of sense. And I'm glad it makes sense. So thank you very much, Leonardo. That saved me a lot of time for sure. I guess 2 resistors is enough. Oh, you know what? No, I need to check. I need to check the voltage because I want to see how they drop across these. So I'm gonna take out my little post, I'm going to add one of these little cables here. Does this yellow guy reach? He almost does. So I'm going to just shift this to wherever he does reach. So we have 18, which he doesn't want to go in there. Maybe he wants to go into 11. All right, 11 to 18. Boom. All right. So we have 11 to 18, but there's still no connection, right? Because 9 is the end of the resistor B. So I'll just move him and send him into 11. So right now the power, when it's on, should go out positive, into resistor A, out resistor A, into resistor B, to the cable, yellow cable, takes it down to the other cable where it goes to ground. Again, all of these rows are connected, right, automatically. So what to do here? Turn it on. All right, so we turn on our power. Bloop. Right now it's powered up. Just imagine you hear like bzzz, like a sound effect from a video game or something. And we're gonna take our voltage. All right, so voltage, I'm gonna do solid, what do we call this? It's a whole number? Like it's not a single digit, but it's in that range. And let's start touching stuff, right? So we know that we have 3 volts from the source. We have 1.55 on this dude, and the other guy we have 1.54. So that's pretty interesting. It's split evenly, which is what we would expect, right? And if I go from the first guy to the last guy, I should have the full 3. So I'm starting to understand this at least a little bit. We have the full voltage across all of the components. It's split among them. But when we take measurements of each individual one, we'll see how much voltage they're consuming. Now, I don't know if consuming is the right word for that. I don't know if they're eating this voltage or what. But yeah, so that's a great little thing for me to know, because I really need to be able to take accurate readings and understand what's happening as I move forward. So that's a really good thing. So thanks again, Leo. That was a great insight for me